Good morning to all of my students. Today I will start Unit 2, Lecture number 9. Unit 2 and Lecture number 9. So, in this lecture we discuss about binary relations and very important results regarding binary relations, and also we discuss about partial maps and some relevant results. In this lecture we deal all with this. Now let's start. See, X is a non-empty set, correct? So when we say that R is a binary relation on a set X, R is said to be a binary relation on a set if R is a subset of X cross X. This we know before that. So R is said to be binary relation when R is a subset of X cross X, correct? Now, one X, that is X comma X, such that X belongs to X, this is called identity relation. X cross X, this is called universal relation. So both are binary relation. X cross X is also a binary relation, and 1X is also a binary relation since it is a subset of X cross X. But this is called equality relation. And this is called universal relation. Now, what we do, we just collect. This is the set of all binary relation. Set of all binary relations on set X, correct? Now this is the set of all binary relation on set X. Now we prove that we define operation on this like this. This is an operation, and how we define? You take two binary relation rho comma sigma belongs to Bx. Now we define composition of these two relations as X comma Y belonging to X cross X, such that there exists Z belongs to X, such that X comma Z belongs to rho and Z comma Y belongs to sigma. See, how we define the composition? Rho and sigma are the binary relations, correct? Now we define composition, that is rho composition sigma is equal to X comma Y belonging to X cross X, such that there exists Z belongs to X, such that X comma Z belongs to rho and Z comma Y belongs to sigma. So in this way we have defined the composition of two binary relations, and you see that this binary relation, this is a binary. This composition is binary operation. Why? Because rho composition sigma is rho composition sigma is a subset of, you see, X cross X. So being subset of X comma X, rho composition sigma belongs to where? Bx. It means rho composition sigma is again a binary relation. So being a binary relation, it again goes into the same set. So now we prove that set of all binary relation on set X forms a semigroup with respect to this composition. We prove this. So your next result. Proposition 1.4.1, 1.4.1, page number 16. That is what you have to prove. Basically, you have to prove that Bx with respect to this operation is semigroup. This is the result. We have to prove this set is a semigroup. Of course, obviously, if you take any row composition sigma belongs to Bx for every row comma sigma belongs to Bx. This is true by the definition of row composition sigma, of course. Clearly, this is true. Now what we have to prove? We have to prove associative, that this operation is associative. We have to show that row composition sigma composition tau is equal to row composition sigma composition tau for every row sigma tau belongs to Bx. So this we have to prove it. So you have to prove that you have taken three relations rho sigma tau. Now you have to prove associative operation is associative. You have to prove this. Now what you do? You have to prove this is equal to this. So take element here. Take any x comma y belonging to row composition sigma composition tau. Of course, row composition sigma composition tau is a binary relation. So being a binary relation, it contains appears x comma y like elements. Okay, so we take any arbitrary element here. Now you see that it implies x comma it implies there exists z belongs to x such that x comma z belongs to row composition sigma and z comma y belongs to tau. Is it clear? So x comma z belongs to row composition sigma and z comma y belongs to tau. See, because in between if we apply the definition of composition, it will be this. Correct? Now what does it implies? X comma z belongs to row composition. It means what? There exists, you say z dash belongs to x such that x comma z dash belongs to row and z dash comma z belongs to sigma and z comma y is of course belongs to tau. Now you can club these two, combine. It implies that there exists z dash belongs to x such that x comma z dash belongs to row and z dash comma y belongs to sigma composition tau. Now it implies that x comma z dash and z dash comma y. So it means what? This is one relation, this is another relation. In between there is z dash. So what happens? So x comma y belongs to row composition sigma composition tau. Correct? So in this way, you see that you have taken element here and you have shown that this element belongs to this. So it means that row composition sigma composition tau is a subset of row composition sigma composition tau. Also you can go in a reverse way, that is like this. If you start from here, you will reach here. So it means what? It implies it is proved, which implies what? Is semigroup. So finally we have proved that set of all binary relation on a set X forms a semigroup with respect to the operation defined. Correct? Now there are several definitions we discuss. for each row belonging to Bx, we define domain row as x belongs to x such that there exists y belongs to x, x comma y belongs to row. Correct? So in this way domain row is defined. Domain row for each row for each binary relation row, domain row is what? X belongs to x such that there exists y belongs to x, x comma y belongs to row. And now image row is defined as y belongs to x such that there exists x belongs to x and x comma y belonging to row. Now all of you can see that for every row comma sigma belong to Bx, row subset of sigma implies domain row subset of domain sigma and image row subset of image sigma. So I left this as an exercise for all of you, that row subset of sigma implies domain row subset of domain sigma. This is domain sigma. And image row is subset of image sigma. I left this as an assignment. It's very easy. You take element here and show that it goes here. And you have what? You have row is contained in sigma. Then this is very trivial. Now we define for each x in x and row in Bx, we define x row is equal to y belongs to x such that x comma y belongs to row. Of course, it is a subset of x. Now it's very obvious, you see that x row is non-empty, implies x belongs to domain row. So it's very trivial. I left as an exercise for all of you that if x row is not empty, this set is not empty, then of course x belongs to domain row. And if x belongs to domain row, then x row must be not empty. It's trivial. But trivial things are not just to be memorized. They also should be justified by all of you. Okay, how it is happening, how it is trivial. So find out for that. Now, if A is a subset of X, if A is a subset of X, we define A row as union of A row, where A belongs to A. And for each row in Bx, for each row in Bx, we define the converse of row that is row converse will be what? X comma y belong to x cross x such that y comma x belongs to row. Means row inverse contains those pairs x comma y belongs to x cross x such that y comma x goes in row. But this is called row converse of row. It is not inverse of row, it is converse of row. Of course, it's a member of being a subset of X cross X. Row inverse is a member of Bx. Now there are some again facts. For all rho sigma, rho 1, rho 2, rho n belonging to Bx, these things are true. That is, rho inverse, rho converse of, this is converse of rho, and this is the converse of rho inverse. Is again what? Rho. Second is what? Rho 1 composition, rho 2 composition dots on rho n inverse is equal to rho n inverse composition rho n minus 1 inverse composition rho 2 converse rho 1 converse. And third is rho subset of sigma implies rho inverse subset of sigma inverse. Fourth, domain of rho inverse is equal to image of rho. Fifth, and image of rho inverse converse of rho, image of converse of rho is domain of rho. And X converse of rho non-empty re-implies X belongs to image of rho. So these facts are trivial, and I left as an exercise for all of you. Try this, think about this, how to prove. And for any kind of problem and doubts, all of you are free to discuss me. But I'm sure that all of you can do these very trivial things by yourself. So now we do some definition. An element phi of Bx is called a partial map, is called partial map of X if X phi is equal to 1 for all X in domain phi. That is for every x comma y1 comma y2 belongs to X, X comma Y1, X comma Y2 belongs to phi implies Y1 is equal to Y2. So an element of phi of Bx, see, phi is what? Phi is a binary relation. All of you know that when binary relation becomes a map, all of you know that every binary relation is not a map, it's not a function. When two conditions are imposed, that every element of domain has unique image. No element is left in the domain which has no image. Every element must have image in codomain, and that image should be unique. Then we say that such type of binary relations are a function or a map. Now this is the case of partial map. It may partial maps. So one condition is relaxed in this. That is only one condition. That is, see here the element X has two images, Y1 and Y2. If it has two images, then Y1 must be equal to Y2. It means that every element has unique image. Correct? It may possible that there may be an element in a domain which is not related to element in a codomain. It may possible, isn't it? That is why it is not a map. It is a partial map. So an element phi of a Bx is called partial map of X if number of elements in X phi is 1. That is, it means what? For all X belongs to domain phi. It means what? That X has unique image. For example, if X is related to Y1, X is related to Y2, then Y1 must be equal to Y2 if phi is partial map. Correct? So this is the definition about partial map. I also want to tell you some example. Yeah. If X has A, B,